Okay, part two of our marathon session here. Picking right up where we left off because I just hit stop and then went to upload that and came back. So we're now at layer 3. We're talking about routers, which can do everything that switches can do, which can do everything that repeaters can do. So joins the network. It can see the IP address, so it can see the network or logical address, and now it can filter based on that, and also on MAC. Typically it will do on IP address, but it could also see the MAC and filter based on that. We're going to talk about it filtering broadcasts. So when we get to here, we have routers. When we get to here, there we go. We got routers, layer 3. Broadcasts never pass. Now, again, this is the entire world in 6 colors or 8 colors, so there are some nuances here. I can come up with scenarios, and we could discuss scenarios where broadcasts could pass a router, but in general, broadcasts are dropped by a router. And one of the things that you can think of, if broadcasts did pass routers, the internet would break. Because if I sent out a broadcast from my network and it went to my edge router, and my edge router sent it on to my ISP, and my ISP sent it on to the core of the internet, and that sent it everywhere else on the internet, when I sent a broadcast on my network, the entire internet would have to stop and wait for that to pass. We would have CSMA-CD across the entire globe, and the internet couldn't function. So to prevent that, we can have unicast packets, but they have to be sent to a specific destination, not to everybody. And it used to be an issue locally, like sending out, I could do, let me go to screen. Okay, I could do a ping on an IP address, 255. Okay, so that is a pure broadcast. This says ping everybody. Anybody who can hear me, send this, who's connected to my network, send this out. Prior to Windows 2000, this actually worked, and this would go to every node. Starting, I think, with Windows 2000, I know it was available in NT4. Starting with Windows 2000, I believe, was the first time that it would try to resolve that, and it wouldn't, and it would die. But that is a send a ping packet to everybody who could hear, and we actually could do some damage. Ping actually is one of the #1 attack tools that we have, which is kind of funny because it's on every machine everywhere, and it's a basic troubleshooting tool. We have to have it. You can't disable it. But anyway, it can cause some havoc. So we are filtering, killing all the broadcasts. It actually is going to look at packets and see if there's any damage with them. So, and it will kill those. So actually, if we go back here, it only passes good unicast, potentially multicast, but in this case we're just going to say it passes good unicast packets. So it has to be from someone to someone else, specifically from one node to another unicast, and one of those nodes has to be on my side of, or one side of the interface, and the other destination has to be on the other side of the interface. And if it's a good packet and it's known that the source and destination are on opposite sides, then the device will pass it. Otherwise it will kill it. And so our little phrase is when in doubt, kill it. So it actually is, layer 2 was when in doubt, pass it. Now it's when in doubt, kill it. It's basically the exact opposite. Now, if we go back to, we were only partway done with this. If we go back to if we go back to this scenario and we put a repeater here, this works out so much better on the board because I can erase stuff. Not a repeater, we put a router. There we go. This is like hour 3, I think, for me lecturing, so I'm starting to not be able to see straight. So A passes to B, it's going to be blocked. Remember, with a router at layer 3, when in doubt, it's going to kill it. So the only time it's going to pass it is when it's known on one side to the other. So we're assuming that the routing table in this case is built. B to A, it's going to block. A to G, it's going to pass. G to A, it's going to pass. A to M, it's going to block. It has to see the source and destination in this table, and if it can't see the source and destination in the table, if it's not a good packet, or if the source and the source and destination have to be on the opposite sides. So it has to be a good packet, source and destination have to be known and be on the opposite sides of the interface, and then it will pass it. Otherwise, it'll kill it. And so A going to M was a block. A going, sending a broadcasts are always blocked. Well, blocked, kill, filtered, we're using that. So this was a no, this was a no, this was a no. So the only two, if we put a router there, the only 2 packets that actually passed were A to G and G to A, and that was only after the routing table was completely populated. So if you unplug a router, remember what happened when we unplugged a switch? We unplug a switch, we plug it back in, and it passes everything. And then it passes everything, and then it starts to filter. So it begins to filter. This is layer 2. At layer 3, which I'm going to have to move because you're not going to be able to see, at layer 3, it kills everything. So it passes nothing at the beginning until it figures out where everything is, and then it begins to pass some. Begins to pass some. So they're really, a switch and a router actually functionally are totally inverted. Switch passes everything until it gets smart enough to know that it can filter, and broadcast will always pass. Routers will kill everything until it's smart enough to know that something has to pass, but it still kills all broadcast. So the total amount of packets passing a router is actually really, really small. The total amount of packets passing a switch or a bridge is actually pretty significant. And because this is plus broadcasts, and this is no broadcasts. Okay, no broadcasts. My head keeps getting in the way. I need to move my face to another side because that's a pain in the butt there. Okay, so the rules actually are really important. Now, I've had arguments with people that say that we talked about a layer 3 switch, that a layer 3 switch and a router are the exact same thing. You can call a router a layer 3 switch, and I say no. Now, there are, again, some nuances, and it depends on the vendor, and it depends on how things are set up, but in its generic layout, a switch uses when in doubt pass it, and a router uses when in doubt kill. I don't know why that's out of focus, because autofocus is on. There we go. Okay, so and my rebuttal is, if you think that's true, then you go to your edge router where you plug into, or where you connect to your ISP, and you replace that device with a layer 3 switch or layer 4 switch, and see how long that lasts. Because if that layer 4 switch is passing broadcasts, the ISP is going to get a bunch of broadcasts, and at some point you're going to get hate mail or a phone call, or you're going to get disconnected from the internet. So this underlying rule here, and then this is just bucket passing. This is stupid, no filtering, just garbage in, garbage out. Which actually is not worth the time that it took for me to write that. But the when in doubt pass it versus when in doubt kill it is a really, really significant piece of this. I don't know why someone's running upstairs, but they are. that causes issues. Now, we go back to VLANs again. VLANs allows me to have virtual or multiple broadcast domains. Allows me to subdivide the broadcast domains, which I can't do on a layer 2 device. Normally, I would have to pull in a layer 3 device and route. If I put a router in its place, then I lose some of the other things because broadcasts aren't gonna pass. But I'm also gonna have other issues because some of the other packets aren't gonna pass. If we're in doubt, it's gonna kill it instead of passing it. Okay, so the rules are important. Again, VLANs we'll come back to again, and I'll review that when we go over the review. So we did layer 2. Let's go back to, we kind of left off here. Can I do that? Can I? Okay. Hopefully that worked, that I just dragged myself to the other side. So for A, we've talked about this. Somebody in A sends a message to somebody else in A, and as long as the learning bridging table is, we're doing collision domains, so I need blue. As long as my learning bridging table is populated, somebody in A sends to somebody else in A, it's not going to pass the switch or bridge. Somebody in B sends to somebody else in B, assuming it's populated. Somebody in A sends to somebody in B, or somebody in A sends to somebody in C, which isn't even connected here. So we could have this, or this, or this. It just depends on the scenario. Can't have them all at the same, well, we could have these two at the same time. We couldn't have the other two at the same time because CSMACD would throw a fit. Now, broadcast domain, somebody in A sends out a broadcast. Layer 2 devices always pass broadcasts, unless they're multiple VLANs, and that's beyond the scope of what we're talking about here. So broadcasts are always like this. Okay. Now, we go to layer 3 device in the middle, A on this side, B on this side. A sends the message to somebody else in A. B sends the message to somebody else in B. A sends the message to somebody in B, and it's valid. A sends a broadcast. Broadcasts never pass the router. Somebody in B sends a broadcast. So we'll always have 2 broadcast domains separated there because the broadcast will never pass that router. Again, asterisk. There are a few exceptions to that, but we're not going to cover those now. Somebody in A sends to somebody else in A. The router is not going to pass it because it doesn't have to. B to somebody else in B, it's not going to pass. A to B, it's a good packet. It's a good unicast packet destined for somebody on the other side of the interface. It is going to pass it. So I do have the option of having multiple broadcast domains, and these 2 conversations could happen at the same time, just like these 2 conversations could happen at the same time. These 2 broadcasts actually could happen at the same time. But that's the collision domain, broadcast domain breakdowns for layers 1, 2, and 3. All right. So, okay, we did the when in doubt, kill it already. We did the when in doubt, kill it. See, I don't even know what screen to look at anymore. All right. Filters damaged packets, communicates with local hosts and remote routers, but not remote hosts. So it's interested in getting, if you think of mail delivery here, your post office and your mailman is interested in getting mail destined to you, getting it delivered to you, and it's interested in getting messages not destined for you to whatever zip code. Sorry, I'm OBS there. OBS just freaked out just for a second. They're interested in getting it to the correct city. So if it's not, I live in Mattoon. If it's not a Mattoon address, we want to get it to the right city. If it is a Mattoon address, we want to get it to the house, the correct house. So that's why we communicate with local hosts on our own local network. And if it's not destined for our network, we're going to talk to the router for that network to try to get it. And then it's up to them. It's that router router that's going to get it to its own local host. We have routing protocols that we use to get them there, and we're not going to talk too much about those. We got two different types. Distance vector, which primarily we'll use RIP. When we get to TCP/IP, we'll talk a little bit about these. When we get to advanced routing, half of the advanced routing class is over RIP1, RIP2, OSPF, eGRIP. Trying to think of what else. And so we actually set up and configure these on routers. We don't do we do some switch configuration, but not a lot. But most of that, because it's advanced routing, most of the class is router configuration. Now, RIP is distance vector. Distance vector is, and both of these, all of these are what's the best, most efficient way that I can get this. We'll go back to the post office. I deliver something that's going to go to Ohio. My in-laws live in Ohio. Let's say I'm going to send them a letter. So I put in their zip code and I deliver it to the post office. And they look at that zip code and they say, hey, that is not Mattoon's zip code, so we need to get it there. Now, how can we get it there? And they will have a map that says, if you're going to go to these zip codes, this is the next destination. And that's essentially what the routers will do. The routing protocols will talk to each other, and they will have a best path determination for whatever packet it is. And this is distance vector, which means the best delivery route is the least number of routers that I have to go through. So it might not be the best, and I think we talked about this before. MapQuest taking it to Cluthe, the shortest number of miles was actually going down 45, but the best path is actually I think we talked about RIP and OSPF already, that the best path was actually the faster, better way to do was actually on the interstate, and that's really kind of like OSPF. So this just says the number of hops or the number of routers that I actually have to pass through. The lowest number of routers I have to pass through is the best path, and that's how I'm going to get it there. RIP is simple. It's not very chatty. It runs on really old, cheap equipment, router-wise. I mean, you don't have to have a super high-end router to run RIP version 1 especially. And we have 1996 version 2690s, I think, that we were running them on, and we can do RIP 1, RIP 2, OSPF, and they all work just fine. And actually, we're doing them now in emulators. Which I got kind of lucky because in advanced routing, we had used PC-based emulators for to emulate the routing environment, to do all the configuration. And I had just gotten everybody transitioned to doing all of our routing homework and everything else on the emulators, and then we shut down, which meant that if we wouldn't have done that, we would have had to come into the lab and had the physical routers to deal with. So it wasn't forethought, because I didn't even think that would happen. I just got lucky that we had. For me, it was easier because everybody got multiple routers that they could configure. So anyway, you're going to benefit from that because it's all set up and we know it works, and the labs are all basically done. So it'll be a little bit smoother. It was kind of chaotic because Bill had just retired and I took over both of those classes, and so I was about one step ahead of the class because I had to design the labs, build the labs, test the labs, and then produce them, publish them. So there was a lot of I did a lot of work for that. Learned a lot too. I thought it was fascinating. And I think almost everybody went through thought it was not only fascinating, but you got to set it up from the beginning. So when we did it in the classroom, there was usually a team of 2 or 3 that set it up, and so you only did pieces of it. But when you had to do the whole thing, it made a pretty big difference. All right. Anyway, OSPF, open shortest path first. Kind of a stupid name because it's really not the shortest path. Sometimes it could be the longest physical path, but it's actually a more optimized path. It's called link state algorithm, and you will need to know for the Net Plus that RIP is distance vector and OSPF is link state. Link state is essentially the length, the number of hops plus the condition that's going on. It's more complex than that actually, but for this class we'll say it's hops plus condition. So this is RIP is kind of like just looking at the map and seeing the minimum distance, and OSPF and link state is like doing traffic updates to find out that, oh, there's an accident on there, or the speed limit, or there's some stop signs, or it actually is more efficient to go the other route. So OSPF is chattier. It takes more horsepower to actually pull off, but generally it is a better, more efficient. It will get your data to its destination better and quicker. It also is scalable way more than RIP is. So you can have zones, and in an enterprise situation, in a large network, and both of these RIP and OSPF are internal routing protocols, so they're designed for enterprises that have a fairly extensive network. We at Lakeland use RIP, and it works out fine because we're small enough. We don't have that many. Most of our network is switched, so we don't have a lot of routers anyway. So but anyway, OSPF is a full chapter. We have RIP version 1 is a chapter, RIP 2 is a chapter, so we configure both of those, and then we go to OSPF, and then most everything else is a combination of one of the two. It takes the best of this and the best of that, or some of them combine. Takes a little bit of RIP and a little bit of OSPF and adds them in. We can have redundant loops, and there was a sheet somewhere. Yes, we go back to, remember this looped layout? Well, instead of using spanning tree, if we use routers, I'll just do those here. So if we had network 1 and network 2 and network 3, and we had routers, I'll put routers there. Now my head is in the way again. Okay. 1 and 2 and 3, and we have routers in the way. Those routers are actually going to use, we'll assume they're going to use RIP or OSPF to figure out. And if somebody in 1 wants to send something else to somebody in 1, it's never going to get out of here. It's going to be, in that case, the collision domain would actually be just that. 1 wants to send to 2, the collision domain is going to be there. 1 wants to send to 3. 1 sends a broadcast is never going to leave. So the broadcast domains here look like this, and the collision domains are either the individual ones, or somebody in 1 talking to 2, or somebody in 1 talking to 3, or somebody in 2 talking to 3. So you're never going to get that situation where you have a looped layout. The routing protocols also have packets have a TTL, a time to live. So even if for some reason they got caught in this, let's say it's a really complex web of interconnected nodes and it wanders around, there's only so many. RIP, I think, has a TTL of 16, so there's only 16 routers they can actually track through until it kills it. So it makes sure that packets don't stay out there. And these are packets running at nearly the speed of light. So packets are not going to be on the network very long before they actually are snuffed out. You can change frame types, and you can change basically anything at layer 3, 2, or 1 with a router. And so you'll see fiber uplinks in a router. It said it was going to cost over $1,000 for me to put a fiber uplink in our switch. That's a layer 2 changing layer 1. We could do the same thing in routers, and a lot of times you'll see routers that actually have plugins, and our enterprise switches just have a dock basically that I could change out. It doesn't come populated when you buy it, and so if I had, because there's so many fiber and other connectors, I could have ST or SC or MTRJ, and I could just buy the adapters on it and plug them in, and they would automatically seat and automatically work, instead of having to buy, we just bought a bunch of ST routers and now we're going to switch to MTRJ. We have to throw those away. We just pull that connector out, and I have those in class. It's one of the things I'd like to show you, and it's not terribly important, not even enough to Google it, but the higher end equipment typically will have that, and it'll have modules that when they get upgraded you can pull them out and you can redo them. Okay, that was routers. Let's talk about routers for a second. I love browders. Browders are the things you think somebody's pulling your leg. So a browder is a bridge slash router. So let's talk about. God, I did it again. Okay, so browders. So it is a bridge slash router. It has capabilities of a router and a bridge. And you think to yourself, but Scott, you said a router can do everything that a bridge can do and that a hub could do, or that a repeater can do. Why is this? Well, here's the deal. Oh, wait. Hey, remember this? Okay. Hey, here's something. I'm going to add this in heavy green because this is not on our sheet. So we do have, there's RIP and OSPF, and we have TCP/IP. Oh, no, we do have it. TCP/IP and SPX/IPX, and we have NetBEUI. Okay, so NetBEUI did not have, because it's not routable, it did not have a layer 3 component. And technically speaking, so we're getting a little more sophisticated. Technically speaking, NetBEUI works at layer 4, but it has a little bit of layer 2. It actually uses the MAC address, so it has the ability to do both 4 and 2. It just doesn't have anything at layer 3. So what a browder does is, if it's TCP/IP traffic and there's content and addressing at layer 3, it will route it. If it's NetBEUI traffic and there's no layer 3 addressing there, it'll drop down and it will bridge it. So it will treat it like it is a layer 2 device. So if the routing information or the IP address, if the network address is available, it will route it. If the network address is not available, the MAC address will be available and it will bridge it. So that is the function of a browder. Now, that being said, originally we used to have browders. And I had a browder at one point in the lab because we had that environment. We had TCP/IP in its early stages and NetBEUI when we were originally going. We had well, I would say I never had a bus network. I did Star Ethernet from the beginning, but in the early days, we had routers. Today, most of your routers have browding capabilities. So they have the ability. It's usually a checkbox that will say bridge NetBEUI, and you check it. And then your router has become a browder. So in 10, 15 years maybe, we really haven't talked about a browder as a device. In fact, let's even see. Can we? Let's do browder. Router. B router. That's pretty funny. Okay, so don't look at that bridge router because that's not what we're doing. That actually is a wireless bridge. So basically everything in wireless, they call it wrong. Router. A network device that acts as both a bridge and a router by routing packets from known packets and forwarding all others. Yep. So I'm not seeing. Wow, those are not the pictures that I was thinking that I would see. You gotta be careful when you go to Google Images when you're teaching. Okay, so back to the notes. All right, so browders, most routers have the ability to have that configuration. You just have to go in, and I'm talking like enterprise class routers. I'm not talking about your router at home. Your router at home is going to want to kill NetBEUI for the most part because it doesn't need to pass it, unless you have a really. I don't know that I've seen. I think I've only seen browsing capabilities on enterprise grade stuff. We'll assume it is. And usually, again, it's a configuration checkbox in the interface when you set it up. Now, gateway, we'll talk about IP gateway. The IP gateway is your traffic, your portal to the outside, the router that you would talk to get to the outside world, whatever that is. That's the IP gateway. This is different. Okay, so this gateway is an OSI 7-layer gateway. This is it's either hardware or it's software or a combination. Usually it's a combination. It translates between two different things, and generally speaking, gateways will work at all 7 layers. So it is a universal translator that lives in 2 worlds. Let's say I was born in China, grew up in the United States. I understand Chinese culture and I speak Chinese fluently, but I also understand American US culture and I speak English fluently. I would be a gateway. I can live in both worlds, I can talk to both worlds, and I can translate data from one side to the other. That's when we're talking about a generic gateway. That's what we're talking about. So we've got SNA systems would hook a mainframe to a regular network. Emails used to have gateways. We don't have anymore, but we used to have Lotus Notes needed a gateway to get out. Otherwise, all of the attachments were garbled. Is it NetBUI to AppleTalk? NT had their NetWare. We'll talk some in survey class and then some in server class about Windows NT, and it had this NetWare gateway, the gateway for NetWare, that basically it started out as a bridge to translate between the two, and then one of its components would actually emulate and pull information from a NetWare server. And so basically it would allow you, if you had a NetWare server on your network, it would vacuum out all the pertinent information and transfer it to the NT server so you could shut the NetWare server down. It was really, I mean, technically it was really cool. It was really useful. If you had a NetWare network and you would then you were in the transition mode to NT, it's, as a technician, it saved a ton of work because it went out and it would pull all your users and different accounts, and it garbled permissions somewhat because the permissions on both sides weren't the same, but it would save hours and hours and hours of work on an enterprise network pulling those over. If your boss said, hey, we're NetWare and in 6 months we're going to need to be, everything's going to be transferred over to a Windows NT box, this you would run and it would go out there, and in 10 minutes basically most of the job was done. And that this gateway for NetWare from NT Server was probably one of the tools that actually killed NetWare faster than anything else. Oh, and I just noticed that W should be capitalized. And nobody's heard of NetWare now, but it used to be, it was the big fish in the pond when Windows Server was the small fish. We had Unix and NetWare, and then the little bitty guy was Microsoft. And this tool did more to flip that around so that Microsoft went from having like 25% market share to 75% market share in 4 or 5 years. And Y2K actually did a lot of that. I mean, that's when most companies dumped their NetWare boxes. So that was a time for that. So gateway is just a universal translator. When we're talking about that, when we're talking about an IP gateway, we're talking about the IP address of the router that you would use to get to the internet. So 2 different terms, you have to know its context on that. And we're done with that. All right. So we've gone through all of this. We've gone through collision domains and broadcast domains, and we will review those, and I'll show you. I've got another handout. It's actually a really old Net Plus study guide from long ago that actually does a good job talking about that. We had the 3 layers and the rules and what goes on there. We'll do a little bit more with VLANs on the next one, but the next thing we have is going to be we got a bunch of little minor things, review, getting ready for the midterm. So that'll be I'm expecting that's the next video, and I've already posted the list. I'm going to go through. We've covered almost all of it. One thing before we go. For the midterm, and normally in class I'd say what's going to be on the midterm. Well, what have we covered so far? It's going to be topologies. It's going to be OSI. It's going to be a lot of OSI. Cabling, going to be a lot of cabling. Devices. Some protocols, we haven't talked a whole lot about protocols, but that's the lion's share of what we've got on there. I thought I had, yeah. Let's just bring this down. So topologies, if, there we go. View, zoom, 200%. All right. Topologies, OSI layer, cable specs, devices, and their functions. About 50% of the midterm comes from those 4 topics. That's the majority of what we've been talking about the last 3 weeks, something like that. We've done a little bit of 802. We'll go back through MAC addresses. We'll talk a little bit more about protocols. Networking terms was like attenuation and baseband and broadband. We haven't really talked about organizations. I have to go back and pick that up. We haven't talked about structured cabling subsystems, and I haven't mentioned the 543 rule, which is not that important these days. This book reading is actually out of the physical book that you have, so this will be a good review, and you could start on that now if you wanted. Those are the pages, for the most part, they are the pages we've already covered, or very close to the things we've already covered in the first 3 chapters. It's just, I mean, you can see it's just spread out a whole lot more. But those will be the pages you want to review before the midterm. We'll also have to do a practice test to make sure that the lockdown browser works, and I need to hear from everybody to see if they have a webcam that they can use, and how we're going to do that, because the midterm is going to have to be in that lockdown environment. Okay, I think we're done. The next one's going to be running in detail down through this list, and I'll be just kind of picking up a bunch of miscellaneous topics to make sure that we're good, and then we're ready for the midterm. After the midterm, we'll do conversions and start in on IP, and that's about when we went to lockdown in the spring. So from just about right after the midterm is when I've got a lot of stuff already out there. Now, at the time, about mid-February, I got a sinus infection, and it got backed up, and I probably should have gone to the doctor in early March, but I didn't. And then we went into lockdown, and then I was kind of stuck. And so I was basically like, one nostril was clogged from my left nostril, I think, was clogged from middle of March until early May, when I finally went to the doctor. They gave me some medicine. In about 3 days it was gone, but I really struggled. So I'm going to have to redo the lectures anyway, but the content is going to be out there. I'll just start unlocking it. So we should be able to get through. I'm trying to get as much content posted as quickly as possible so you guys can go through and get ahead of the game. I'm being a little aggressive on the dates, I know, to try to get through so that we've got extra time. But if as we go through, if I stay on this pace, I'll kind of stretch the deadlines out just a little bit. I don't want to get behind. There's a lot of content here, and I've tended to do 2 or 3 lectures in a stretch in a particular day. And then I've got other things going on that I have to do. So I'm assuming you guys probably will do the same thing and kind of take these in big batches as well. All right. Next time we'll go through this study guide, and you should have homework. I'll probably post some homework over I'll probably post it when we cover this. So I'll probably wait until we do this next thing, and I'll post a little bit more homework. Then we'll be ready for the midterm. All right. Talk to you next time.